Hello students, welcome back. Let's go to section 3 now, interval estimation for population means. Here, we can see this distinction to the full. If we know population standard deviation, then you can use SC equals sigma over square root of n, as in central limit theorem, and then use the normal approximation. You can use the standard Z table. But most of the time, you don't know population standard deviation, nor the population mean. What do you do then? We replace sigma by S, which is the sample standard deviation. Will it still work? If the sample size n is sufficiently large, yes it will. Again, the same reason, the central limit theorem. If n value is not very large, in that case we have to use an alternative method. That alternative method is something we are going to discuss here. Here's a checklist. Is sigma known? Yes, then you can use normal. No, ask this question. Is the original population normally distributed? Yes, then you can use t-distribution, which we will study. If no, then you have to have really large sample size and use normal. Otherwise, everything will go moot. So what method are we talking about? Student t-distribution, which is based upon something called degree of freedom. I think there's something wrong here. Okay, I got it back. Where was I? Yes, student t-distribution, which has density function as in this blue curve, and the red dotted curve, by the way, is a z-curve. And it depends upon sample size. The degree of freedom is n-1, and at this level, in 3000 level, degree of freedom will be n-1 because we're going to deal with one-dimensional examples only. Well, maybe not only, but most of the time. If you go 2 dimensions, sometimes you see n-2 and so on and so forth. But here in 3000 level, n-1. Okay, there are some exceptions that we'll have to discuss sometime in week 13, I think, but for now, let's just keep it simple. Degree of freedom, n-1. So, here in this visualization, we have various degree of freedom. So, degree of freedom 1, so sample size is 2. We have this curve. Nu is 2, and blue curve went up a little bit. 3, 4, 5. As you can see, blue curve approaches the normal curve. And if nu goes to infinity, then the limiting curve will be the z-curve. So if the sample size is sufficiently large, then it's okay to use the normal curve. Now, how do we utilize TCurve? Well, let's go to an example problem. The pulse rate of 13 adult women were as follows, and then we have this data. And then from here, we can find out the mean. And the sample standard deviation. So mean is 75.6923. That's easy. Add up all these and divide by 13. That's it. Standard deviation is far more difficult to calculate. Basically, you'll have to do this. So 83 minus this squared plus the next number, 58 minus this squared plus and so on and so forth, and repeat it 13 times until all the way to the end, and divide all these by 13 minus 1, and then we have to take the square root. Do you remember this? Of course, you don't want to do this computation with handheld calculator. It's much better to use technology, which I just did. So we have the mean and sample standard deviation. With these, let's find some confidence interval. All right, how about a 90% confidence interval? Here's a visualization. In the middle, we have 90%. So 90% of chance that my interval estimate is correct. That means 10% of chance that I'm wrong. So the real mean is too large or too less. So red part here or there. And the idea is the same, basically. We want this computation. T-score, just like Z-score, is n minus center over SE. Let me expand the font a little bit further. And that n is the quantity we want to find out. Let's see, left-hand side L, right-hand side R. Let's use R, right-hand side. And the center here is the point estimate. In this case, 75.6923. All right. Divide by standard error. It's going to be S over square root of n. All right. I also be premature here. Let's use that expression. And then now let me put in numbers. So right side endpoint minus 75.6923. And then divide by standard error 14. Oh, I forgot. 5395. 5395 over square root of 13. And this is your t-score. And if you look up your t-table, you're going to get appropriate number. And from that, you can solve an equation to find out the R value. All right? Now, big question. How do you look up the t-table and get this t-score? Let's discuss that. Here is the t-table. And z-table looks like this, shaded to the left. T-table is shaded to the right. And then you have degree of freedom on the left-hand side. That's n minus 1. So in this case, sample size was 13. So degree of freedom is 12 in this case. No, too big. And then we want, I forgot, 90% confidence interval, so 5% here. So let's look at 5%. So this part is 5%, and that's coming from this column here. So here we go. 5% and degree of freedom of 12. So what do we have? .782. That's your t-score. Does it make sense? 1.782. Degree of freedom 12, and then this probability is 5%. 90% in the middle, 5% left, 5% right. So 0.05 is there. 1.782. All right, 1.782. So this one is 1.782. From here, looking for R value, that's not too bad. Let's copy and paste this thing here. I don't need this part. Flip the denominator to the other side. We get this. T-score times SC, the margin of error. And flip this point estimate to the other side too. Then this is what I'm going to get. There you go. And if you calculate this, you're going to get your right-hand side endpoint value. Let's see. 82.8783. All right. That is the right-hand side endpoint of this confidence interval. Now, what if you want to find out the left-hand side endpoint? Do we have to start over? No, you don't have to. Just use symmetry. Just use symmetry. What do I mean by that? From here, I went right plus margin of error to get the right-hand side endpoint. From the point estimate, from the center, let's go to the left. Just subtract, and that's it. Of course, if I run the calculator, you're going to get what I want. So there goes the confidence interval. Make sense? Center minus margin of error. Center plus margin of error. Center minus t-score times SE. Center plus t-score times SE. Except for z-score versus t-score, exactly the same structure. Similar picture, in hand-drawn picture, it's going to be impossible to distinguish one and the other. Let's review the computation through my answer key here. Yeah, it's the same deal. That, and then SE computation is here, S over square root of n. And n minus center over SE is my t-score. And here, left-hand side and right-hand side endpoint, I considered both of them simultaneously, plus or minus 1.782. Yeah, that's fine too. In the end, we get the interval like this. You can use parenthesis or bracket, it doesn't matter which way you do. One more comment about the t-table. Let's go back here. And what did he do? 5%, and then degree of freedom 12 to find out 1.782 here, right? 5%. But if you scroll down, that corresponds to confidence level of 90%. That's natural, 90% in the middle, so 5% to the right, 5% to the left. So you can start from either down here or from up here. It doesn't matter which way you do. Me, I usually start from up here, and because that's associated to the picture, but a lot of students start from down here. Either way, it's fine. Can you do the same thing for 98% confidence interval? Well, that's left to the students. All right, 98%. So this is 90% confidence level. So I want 98%. So let's run it again. So middle, now I have 98%. 1% here, 1% there. And all the answers are already here. Pay no attention to those yet. And then as for your solution, well, let's see. Same sample statistics, same standard error, S over square root of n. And then n minus center over SC is your t-score, but that should be associated to not 5%, but 1%. All right? 98% in the middle, so 1% to the left, 1% to the right. So let's go to that table here. Let's go to 1%, so that's this column. And degree of freedom is 12. Let's see. 1%, degree of freedom is 12. So we have 2.681. Is that right? 2.681. That's my t-score. By the way, you can start from 1% here. You can also start from, you can always start from down here, 98% confidence level. Either way, you're going to get the same value, 2.681. 2.681. So T-score is 2.681. So your calculation so flip this SE to the other side. So point estimate in the center minus the margin of error. So minus T-score times standard error. And this computation, let's see, let's leave it to Mathematica, 64.881. So that is your endpoint. Now change this to plus, and 86.50. So I'll say 64.9 to 86.5. That's going to be my 98% confidence interval. So the same as Z analysis, same type of picture. In hand-drawn picture, they are indistinguishable. And then same Z-score or T-score computation, N minus center over SE. But looking up the table is a little bit different. T-table is shaded to the right, while Z-table is shaded to the left. So I usually take the right-hand side endpoint first. And then you need degree of freedom. All right, how about some confidence bound problem? 95% upper confidence bound. Here's a visualization. Oh, it's already here. 5% here, and then nothing, just all blue. So if you look at 5%, actually this is the same as this problem as far as the T-score is concerned, 1.782, but not minus 1.782, only plus 1.782. Actually, you have to get plus 1.782. Sorry about the typo. Plus or minus is wrong because this is upper confidence bound. For lower confidence bound, of course, I'm going to need minus. So, okay? All looks okay? All right. How about the next problem? Lower confidence bound. Oops. Here's visualization. And 1% there. Now, if you look up the T-table, don't panic. Shading is always to the right. Oh, I don't have a shading on the left. What do I do? What do I do? What do I do? Don't worry. Just use a symmetry. Just find out your T-score from here. 12 and then 1%, 2.681 as you found out before. But you just put a negative sign to it, so you have to go to the left. All right, left as an exercise. I said too much. I shouldn't have said that. I should have let you work on it. All right, use symmetry, and that's where I'm going to stop.